I'm happy to finally have Shaddin speaking here today. So Shaddin is just
Shaddin, by the way.
Shaddin. I'm sorry. Shaddin is just completing a sabbatical year here in Chicago. So when he's not in Chicago, he's in sunny California and USC. But he decided the weather is too good. He wanted to spend some time in Chicago to experience real weather. And many of you have maybe seen him here throughout the year. Also spent some time in was mostly based, I think, in Northwestern and across the Midway in BSI. Shaddin is still here for another few months up until June.
And about a month and a half.
Month and a half.
Yeah.
So if you haven't had a chance to talk to him yet, but want to after this talk, then you can still find him. He's here frequently. But let's see who's going to tell us about the instance optimal learning.
Thank you, Nati. So like Nati mentioned, I'm wrapping up my sabbatical at Northwestern and U Chicago, and then I'm going to go back to sunny LA. It's been a very nice time here despite the weather, and now that it's getting nice, I'm going to have to miss much of it. So I'm going to tell you about relatively smart learning, which is a new approach for instance optimality. And this is a joint work with Alireza Fathoulahpour, who is at the University of Waterloo. He's a fantastic PhD student I've been working with for the past, it's got to be more than a year now. This is my first time giving a talk on this paper. And actually, this morning I found out it got accepted to Colt. So I'm going to give this talk with renewed confidence. But I will say this is a paper that I found pretty challenging to understand and write as we were doing the writing process. And it's also been quite challenging to kind of really interpret the results. So my hope by giving this talk here is I'm going to get some perspective from the people here on how to really interpret what we found. Okay. So my motivation here is trying to get beyond the worst case analysis of learning. So like a lot of theoretical computer science and learning theory, it's common to adopt worst case type assumptions. For example, the PAC model, which many of us know and love, judges a learner by its minimax performance over distributions or its worst case performance. But it should come as no surprise that many distributions that are quote unquote realistic are going to be easy. And that can mean a number of things. One thing it could mean is that your analysis of a standard learner, for example, empirical risk minimization, can be overly pessimistic in those cases when your distribution is quote unquote easy. But even worse are situations where you would want to use a different, less standard learner for these instances because you could do better by going beyond standard ideas like empirical risk minimization. So my high-level goal that I'm going to start with is to ask, basically, to what extent can we get learners that are statistically optimal, instance by instance, or distribution by distribution? Okay. And I'm going to be mostly concerned with statistical optimality in terms of sample complexity rather than computation in this talk. So one way to interpret this goal is that I would like to do as well as if my learner was perfectly adapted to the distribution, even though I don't know the distribution upfront. And by the way, please do interrupt me with questions anytime you want. This is a kind of a good size audience for that.
So just to go first, so this is the distribution is, you're only talking about the input distribution. So it's the worst case on the hypothesis class?
I'm going to get into that in detail, okay. Yes, exactly. Every time I'm saying distribution, I'm going to end up focusing on the marginal distribution of unlabeled data. Any other questions? So I'm going to ask these questions in what is basically the simplest setting of learning, which is just realizable binary classification. So let me give you a very high-level view of what I'm going to tell you about in this talk. First, I'm going to introduce a new framework to you. My starting point is going to be a pretty, not so new, from 2011, but very clever formulation called smart learning, due to Darmstadt and Simon. That's going to be the starting point for my ideas, but let me tell you what smart learning is. A learner is smart if it does almost as well as if it knew the distribution of unlabeled data. This is called often the marginal distribution. When I say marginal distribution, I'm going to mean distribution over unlabeled points or unlabeled featured vectors. So if your learner is smart, it does as well as if it knew this marginal distribution. One way to interpret that is that this learner competes with the best, what we call distribution fixed learner. This is a learner that fixes the marginal distribution up front and caters itself precisely to that learner. Or equivalently, you're competing with what are known as semi-supervised learners. These are learners that have a lot of unlabeled data, so it's almost as if they knew the marginal distribution. So you want to compete with those distribution fixed learners or semi-supervised learners, even though you don't actually get the same knowledge of the marginal distribution. That's smart learning. Darmstadt and Simon showed that smart learning is possible under some assumptions. I'm going to argue I argue some strong assumptions. And this is a beautiful result where they used the minimax theorem to prove that under the assumption that you have a prior on the marginals, you can do well for most of them. I don't have time to get into this result in detail, so this is about as much as I'm going to tell you about it. Of more concern to me is a follow-up work by Darmstadt, Simon, and Zarengi, where they show that smart learning is impossible in general. There are no smart learners without strong assumptions. Any questions? So this impossibility result motivates what the framework I'm going to tell you about, which we're going to call relatively smart learning. So instead of asking you to compete with the best distribution fixed learner or distribution fixed error rate, I'm going to compete only with the best certifiable distribution fixed error rate. What do I mean by certifiable? I mean you can detect that you're doing that well by just looking at the unlabeled data. So in other words, if your distribution fixed learner can't be sure that it's doing well just by inspecting the unlabeled data, then I'm going to let myself off the hook. So I'm going to compete with the best distribution fixed performance to the extent it can be verified from the unlabeled data. So one way I like to think about this is that what we're doing here is we're relaxing our benchmark so that we price in some sort of indistinguishability of marginal distributions. And the goal is that this allows us to circumvent this impossibility result. And this is exactly what we do. We show that these relatively smart learners exist as long as you're allowing them a quadratic blow-up in the sample complexity. And this is true for arbitrary hypothesis classes and in the distribution-free setting. One would hope, oh, and by the way, not just any learner does this. For those of you who know what it is, the one inclusion graph learner is such a learner. One could ask whether you can improve on this quadratic blow-up. We show that you can't. We have a matching impossibility result that says you have a quadratic lower bound on the blow-up in samples if you want to get relative smartness. So those results are for the distribution-free setting. We also look at distribution family settings a little bit. We show that the situation gets a little bit more complicated there, as things often do when you look at distribution families. We show that relatively smart learning can be impossible for some families, which sounds like a paradox because I showed you that it's possible in the distribution-free setting. So how is it that it's impossible when I restrict the family? I'm going to tell you why that makes sense later on. Okay. So it sounds like a paradox. I'm going to demystify it later. So if you're confused, you should be. It will make sense later, okay? I mean, most of the talk I'm going to spend on this, but I'm going to come back to this at the end. If it doesn't make sense at the time, I'll discuss, okay? And also,
the families here is just, okay, it's just the families of input distributions, or there's...
Family of marginal distributions.
just of marginal distributions. There's no. It's not like the. Okay.
Yeah. It was confusing to us too, but now it's not confusing. I'll tell you exactly why. So it can be impossible, which implies, by the way, that the hardness of relatively smart learning is not monotone in the distribution family. I'll tell you more about that later. But also, even when it is possible, it can require non-standard learners that are carefully catered to the distribution family. So I'm going to give you that later. Okay. But for a while, I'm going to focus on the distribution-free setting as well.
So just to get my mindset. So is the issue here? Before I thought the issue was mostly computational hardness, but now when you show this, it seems like it's actually
Everything is statistical.
Everything is statistical. So it's not about So when you say that ERM is hard, this is.
ERM is not relatively smart. It doesn't do as well as if it knew the margin.
Okay. But this is not a so.
Yeah.
It's,
there are interesting computational questions that come out of this paper, by the way, but that's not what I'm going to focus on. Yeah. Any other questions? All right. So that's the kind of 10,000-foot overview. Let me now give you some background and then give you my definitions in more detail. So my starting point is going to be just the standard setting of supervised learning for binary classification. In particular, the PAC model is effectively a good way to think about this. You have a space of instances. These are, feature vectors, sometimes called, features or unlabeled points. Think of them as the space of all pictures that include either a cat or a dog. And then you have binary labels. They can be 0 or 1, or they can be cat, dog. And then you have a family of functions called the hypothesis class. This could be linear functions or neural networks of a particular architecture. And these functions map unlabeled points or map instances to labels. You have an adversary that picks two things. He picks the marginal distribution on the unlabeled data. So this is the distribution over pictures in this example. And also a ground truth hypothesis. This is, I'm going to call it H star. This is the true function that labels the data with cat or dog, for example. Okay. And then the learner gets a bunch of labeled examples. So x1 through xm labeled with H star. And these unlabeled points, xi, I sampled IID from the marginal distribution that is chosen by the adversary. Right? And the labels are given by this ground truth that is a function that is also chosen by the adversary. So far, this is pretty standard PAC learning. Right? And then your learner is going to be tested on a fresh test point drawn from the same marginal. Again, you don't know the marginal, you don't know H star, and your job is to predict the true label according to this ground truth function. What I care about is the error rate of the learner as a function of the number of samples m that it's given. This is the probability that the learner makes an incorrect prediction on this test point. Generally in the PAC model, you talk about high probability guarantees on this error rate, but just to simplify my story, I'm going to talk about expected error rate. Everything extends, but just to get rid of one parameter, I'm going to talk about the expected error rate here. Okay. So what I want is I want this error rate to go to 0 as the number of samples grows large, and this should hold, in the PAC model, this should hold uniformly over all marginal distributions and all ground truth labeling functions, even though they're chosen by an adversary and you don't know, right? That's the usual assumption in the PAC model. And many of us here know that the best thing you could do is the VC dimension of the class divided by number of samples in the distribution-free setting. So far, this is pretty basic stuff. So I'm going to be more concerned with a variation of the PAC model where I give my learner more power, and actually I give it more information. Right? This is distribution fixed learning, studied by Bandic and Itai back in the 90s. This has been called, I'm going to call it distribution fixed learning, but it's also been called the utopian model of semi-supervised learning, because it's as if your learner is given an infinite amount of unlabeled data, so it's almost as if they know the unlabeled data distribution or the marginal distribution, okay? So I'm going to talk about the error a learner incurs on a particular marginal distribution. This is some notation I'm going to introduce to you. So I'm going to define the distribution-dependent error rate of a learner A on a marginal D as a function of the samples. I'm going to denote it by epsilon sub A of D comma M. This is the error that the learner incurs when its data comes from this marginal distribution in the worst case over hypotheses. Okay? So I'm still worst case over hypotheses or ground truths, but I'm going to measure the performance of my learner marginal by marginal. Okay? So in distribution fixed learning, I'm going to assume that this marginal is fixed and I can design my learner perfectly to the marginal distribution. I'm going to say I'm going to cater my learner to the distribution D. So the best thing I could do in that case for a particular distribution D is I could take the minimum overall learners of the performance of the learner on that distribution. So this is what I'm going to call the optimal distribution fixed error rate, or D fixed error rate, epsilon sub D of M, which picks the best learner for that distribution. Okay. And the learner that attains this minimum is what I call a D fixed learner. Sometimes I'm going to denote it A sub D. This is the learner that's perfectly catered to the distribution D for every possible sample size now. So these are the D fixed error rates and the D fixed learners. Now, you could ask, how does this help? It turns out that in the worst case over marginals, this doesn't help you at all. If you remember the proof of the fundamental theorem of learning theory that proves a bound on the performance in terms of VC dimension, you'll remember that proof is robust to actually knowing the marginal distribution for that worst case marginal. So the worst case overall distributions of the distribution fixed error is still VC dimension over M. So knowing the distribution does not help you for the worst marginal distribution. Okay. But for specific distributions or certain nice classes of distributions, it can help you quite a bit. You can actually do much better than VC dimension over number of samples for particular distributions, or perhaps many distributions in a large family. Right? And this can be because a standard learner like empirical risk minimization happens to do better naturally on these easy distributions. Or in more interesting cases, you could actually design a specialized learner. You might have to design a specialized learner for the distribution, and that would allow you to beat the VC dimension bound. Okay. So let me give you a couple of examples. First, a simple one, and then a more involved one. Imagine that my instance space, or space of unlabeled data, has two areas. One area is such that the function class has high VC dimension. Another area, the function class has low VC dimension. If your distribution happens to be supported on the low VC dimension area, ERM will just naturally do better without even knowing that the distribution has this property. So this is where you outperform the VC bound just without actually having to do anything. A more interesting case is when you have to change the learner to do better. And this is my favorite example of this. There's many examples, but this is my favorite one. I'm going to define what I'm going to call the lopsided hypothesis class. And this is where you have a large space of unlabeled points. Think of it as capital N many points. And a hypothesis is one that is either mostly zeros or mostly ones. So imagine that a hypothesis, for example, this hypothesis is mostly zeros except for square root of capital N many points. I'm going to call them the minority points that have a label of 1. But it could be the other way around. It could be mostly ones and if there's a few zeros. And I'm going to allow the minority to be anywhere. Okay? Now imagine that I have a very nice distribution on this space, in particular the uniform distribution. And let's think of how you would do. If you do, what would be the VC dimension here? Can anybody tell me what the VC dimension of this class is? It's actually square root of capital N. Because for any set of square, what's that?
Square root n log n over capital. Okay.
Yeah. It's square root of capital N. Basically, for any square root of n points, I can put ones wherever I want, basically.
So you can choose the places where you can put those. Okay.
That's right. As long as there's, it's mostly zeros, I can put the ones anywhere I want. So the VC bound basically would be trivial for any number of samples less than the square root of capital N. And think of capital N as very big.
No, wait, this is square root of n log n. Why is it not square root of n log n?
I don't know how to shatter a set bigger. Any set of size square root of n plus 1 cannot have, for example, the all 1 pattern.
Any...
If I take a set that's bigger than square root of capital N,
Oh, because
it
these
can't
are your
have all
actual...
ones.
Okay.
Yeah, it can't have all ones, it can't have,
Okay, because
or it
these
can't
are,
have.
because these are your actual...
Yeah.
Yeah.
Oh, actually, yeah, there's definitely a, yeah, okay, what I said isn't true, but you can't get all patterns there.
No, it's okay, the square root of n is...
Yeah. It might be square root of n plus 1 or something like that, but it's definitely not much bigger than square root of. So if your little m, the number of samples, is much smaller than capital N, this is kind of a trivial bound, right? And also, if you do empirical risk minimization, if the learner only sees less than square root of n points, there are consistent hypotheses that have the all zero as the zero being the majority, and they also consistent hypotheses where 1 is the majority. So you could get the majority labeled wrong, which would incur a lot of pretty bad error, right, on the distribution. So ARM does poorly, the VC bound does poorly when you don't see VC dimension many points. But here's a learner that actually does really well, even with a small number of samples. The majority learner, which just always predicts the label that it saw most frequently in the training data. So if it saw more zeros than ones, it would predict 0 for everybody, the 0 constant function. If it saw more ones than zeros, it would predict 1 everywhere. And the error of that learner will be on the order of 1 over square root of n divided by n. Yes?
Why do you need the uniform marginal distribution?
The uniform marginal distribution is an example where I could do better by catering, but actually you don't absolutely need it. It's just the easiest thing to illustrate.
Also, I think it's more about the hypothesis class and not in its distribution, right? It's like sparse label functions.
You're absolutely right. You're absolutely right. But I guess the point of the thing I'm trying to illustrate here is that for some distributions, you could do a lot better by catering to it. It turns out that slight tweaks of the majority learner will be smart in this case, but it's less obvious. Maybe obvious to you. I think it was less obvious to us. But this is a case where catering your learner to the distribution, you can do better. Okay, so now that I have the definition of distribution fixed learning, I can define smart learning, and again, this is due to Darmstadt and Simon. The goal is to compete with this best learner that knows the distribution. That's the goal. Despite not knowing the distribution. You can ask this in the distribution-free setting where this should be true for every distribution, or a distribution family setting where you only care about certain distributions of interest. So they say a learner is smart if for every distribution that is allowed, and every number of samples m, the error of the learner on that distribution is within a constant, a universal constant, of the best error you could get on that distribution. This is the distribution fixed error. Let's remember the definition. It's the minimum overall learners of the performance of the best learner on that distribution, right? It's the minimum overall learners of the learner's performance. So it's basically this picks the best learner for the distribution. So your learner, which is just a supervised learner, doesn't get any additional information. It's smart if, despite not knowing the distribution, it does about as well as if it did, up to a universal constant. And this universal constant can't depend on D, can't depend on M. Any questions? This is yes.
You're learning it in the class?
Yes. But it turns out I don't know of any results where that actually matters. Yes. I think it's allowed to depend on the class, but I don't think it matters for the impossibility results.
So, wait, but that doesn't. No, that kind of.
I think in the original definition, it's allowed to depend on it.
But then, in some sense, you're saying that, I mean, the example you gave before, I mean, the whole
Yeah.
point that, I mean, that you need much less than VC dimension. But this is not captured, if I understand correctly, this is not captured by this definition.
Okay.
Right? You're just saying that, you only care about kind of the asymptotics, the how things decay with M or something. I mean, this is very different than.
Yeah, let me correct what I said. Notice that it's still meaningful to say this for classes that are not PAC learnable. So where this definition has most bite is for classes that are not PAC learnable. And where they have positive results, they actually care about this being a universal constant over all classes.
Okay.
But you're right that if I allow it to depend on the class, I can make the constant trivially large, and that's a good point. But for classes that are not PAC learnable, this is still meaningful, even if I allow it to depend on the class. Yes.
I think my question was similar. So this definition is not about the specific class, right? This is more general definition than.
Yes. So I'm hiding some details. So the original definition says a learner is C smart for a particular constant C, and they care about what C can be. And the interesting cases where C is a universal constant doesn't depend on the class.
For all hypotheses. Universal constant.
So they just allow it the guarantee to be parameterized by this constant, and then it might depend on. You could ask, what attribute of the hypothesis allows you to do it, and what the constant would be as a function of the class. You could ask that. But everything I'm going to talk about is going to involve universal constants. But you're right. This is kind of a subtle point. Any other questions? So smart learning, first let's reflect on it. It turns out it's not easy to compare it to PAC learning. Let me give you a couple of reasons why. You can have a class that's not PAC learnable, but still has a smart learner. For example, if the class is like the class of all functions on an infinite space, it's definitely not PAC learnable, but also knowing the modular distribution doesn't help you either. Right? So in some sense, any non-trivial learner will be smart there because there's nothing interesting you can do.
Wait, I was confused. For any specific distribution.
Yeah, for any specific distribution. For any specific distribution, if you've seen the point before, you predict the same label. Otherwise, it's the best you can do.
Oh, you mean it doesn't help in terms of the algorithm, but it doesn't help in terms of the epsilon. I mean, epsilon dm is definitely less than epsilon m.
Correct, but.
But you're saying that ERM is a smart learner.
ERM is a smart learner, even though the class is not PAC learnable.
Okay.
Basically, you can be smart even though you're not PAC learnable if the class is so unstructured and uninteresting so that knowing the module can't help you.
You can be smart if your opponent is stupid.
Exactly. Being stupid is smart in this case. Exactly
Yes,
right.
yeah.
So I guess this is an example where smart learning is doesn't imply PAC learning, I guess, right? Now, if your class is PAC learnable, if your learner is smart, then it's also a PAC learner because it's doing something more stringent. It's doing well even as compared to the learner that knows the distribution, which means it should also do well in the worst case, but not vice versa, right? A PAC learner is not always a smart learner. Okay, so we saw an example of this, but let me kind of remind you. So typical PAC learners can fail to be smart, even when it's possible to be smart. So remember this lopsided hypothesis class. ERM we know is a PAC learner, but it doesn't have interesting guarantees when the number of samples is below the VC dimension. But like I said, the majority learner does well even when the number of samples is pretty small in this case. And so therefore ERM, even though it's a PAC learner, it's not a smart learner. And I can tweak majority learners carefully to get a smart learner for this class. Exactly like Don suspected. Yes?
Is it totally obvious, maybe I missed it, that the majority learner in this case performs badly for non-uniform distributions.
It's not obvious. The only thing that's obvious here is that the majority learner does much better than ERM. Yeah.
On the uniform.
On the uniform. It's not obvious that it does better on the other ones, but there's a non-trivial thing you have to do.
Okay, so we'll talk about it.
I'm actually not going to talk about that, but I guess the main point of this is just that ERM is not smart. That's all. Okay, so like I said, there's a positive result for smart learning under some assumptions. It's a beautiful result, but I don't have time to talk about it. The more important part for me is the impossibility result due to Darmstadt, Simon, and Zorenyi, where they show that there's a hypothesis class which doesn't have a smart learner. So smart learning is not possible in general. They showed this for a particular distribution family, and therefore it also holds for distribution free, because that's even harder in this case. And this impossibility result is pretty robust. It's robust to giving your smart learner more samples than the distribution fixed learner. For example, you could say, I want to do as well as a distribution fixed learner with m samples, but I'm going to allow myself m squared or 2 to the m or anything like that. Turns out that that doesn't help you. Okay, so this impossibility result is quite robust. Let me give you an idea of the proof because some of those ideas are gonna trickle down into the rest of the talk. It says, their proof is much more technical and necessarily so, but this is kind of a very, it's a caricature of the proof effectively, right? Imagine that for each distribution, let's say distribution capital D, there's only very few interesting hypotheses. So in this picture, the blue hypothesis is interesting. It's got a bunch of zeros and it's got a bunch of ones, so it's kind of an interesting hypothesis. But the red distribution is not really interesting because it's pretty much everywhere zero, except for a small area where it might be one. And if your distribution is, let's say, uniform over this whole space, you could say, hey, you know what, this red function is not so interesting. I could replace it with a constant zero function and not lose very much. So when I know my distribution is, let's say, spread out over this area, I can keep the blue function and get rid of the red function or replace it with a constant function. Okay. But suppose that I don't know the distribution, but all I see are these 3 bolded training points, and then I see this test point, let's say. I have no way of knowing if I'm in the blue world or the red world where the situation is reversed. It could be that my true distribution is this d prime, where the red function is the interesting one, and the blue one is actually mostly zero. So I would have liked to get rid of the blue function instead of the red one. So for those of you who know learning theory, you would want to construct an epsilon cover of the hypotheses depending on the distribution. If you knew the distribution, you'd construct a nice one by basically thinning the space of hypotheses appropriately. But if you don't know the distribution, you don't know how to construct this cover. You don't know that whether you want to get rid of the blue or the red function. Any questions? And the idea is that there's more than 2 distributions in the world. There's so many of them that when I see the training data, it's hard for me to know which world I'm in. So this kind of sets up the key insight that started our paper, is that we can blame this on indistinguishability. Yes?
So are you requiring here the learner is proper or?
No.
So why can't I, given a test point, I can assume this guy know the test point.
Yeah.
Just based on that, see which distribution fits, or assume the distribution is just an empirical distribution over the training and test and
That's right. There's so many d primes that no matter where the test point and training points are, there's always d prime that you could come from. It's just, you're right that if all they had was d and d prime that you would be right, but there's so many of them, so you can't get any kind of uniform guarantee. So imagine these are manifolds and the space of possible manifolds is too large.
Too many, but okay.
I can tell you more later.
I have
Yes?
a small question about the previous slide actually.
Okay.
So here, I guess this example was to demonstrate that PAC learnability does not sorry.
A typical PAC learner like ERM is not smart necessarily.
Oh, he's not smart. Okay.
Not necessarily smart. You'd have to kind of do something specific to get it.
But you did not say that the majority is smart.
I did not say that. That's not easy to show.
Okay.
And actually, I don't know that it is. We had to tweak it a little bit, I think. And honestly, I forget exactly how we tweaked it, but we should probably add that to an appendix, to be honest with you. So how can I interpret this impossibility of smart learning? I claim that it's easy to think of this as a failure of unsupervised learning. Just by looking at the unlabeled data, you can't learn the marginal well enough to emulate the best distribution fixed learner. So it's kind of almost self-evidently a failure of unsupervised learning, this inability to be smart. But what we noticed is that something even worse is happening in the examples we were able to find of this. And that's even if I give you the marginal distribution, you can't distinguish it from different marginal distributions that would need a different learner. So the way to think about this is, if I tell you a marginal distribution but I was lying to you, you won't be able to catch me by just looking at the unlabeled data. Or you can't detect if my marginal distribution, maybe that I learned at great pains from some unsupervised learning procedure, you can't detect if it was misspecified or I did a poor job learning it. So it's somehow even worse than the failure of unsupervised learning. Even if I give it to you, you can't detect if I was lying. So here's an example of where this may happen. Imagine that my distribution, my true distribution is this is uniform over this big blue bubble. And I see a few of these black points. I mean, maybe they came from this blue bubble, or maybe they came from a smaller but still sizable red distribution, which is uniform over a set that includes these black points. So I can't distinguish, even if someone gives me D, I don't know if the points I saw were really from D or from some smaller support distribution that lives inside D. It's impossible for me to tell. Because there's so many different distributions I could draw here, so it could be that these points are from this other smaller distribution. No way of telling. Yes?
But you mean D prime is chosen after the adversary has seen the samples?
You can think of it that way, yes.
Because otherwise
well, actually, if D prime is what I'm going to show you later, if D prime is let's say these are M points. If D prime is a uniform distribution over random M squared points, I won't be able to distinguish it from D. Right. So there's always one.
But you will have a gap between M and M squared.
That's right. And the M squared is exactly where the M squared in my bound comes from. It's a birthday paradox bound. So if you can't distinguish distributions in this way, this clearly rules out smart learning. So what we're going to do is our relatively smart benchmark is going to basically price this in. Right? It's going to basically say, I'm going to give up in those cases, I'm going to do as well as I can distinguish. So looking ahead, by competing with the new benchmark, I'm going to basically show that this indistinguishability is basically the one and only obstacle to smart learning. If you don't have this indistinguishability, you can smart learn, and if you do, you can't. Okay? That's one implication of my results. So, okay, good. So now I've motivated the definition of relatively smart learning. So let me tell you this weaker benchmark that we're going to compete with. This is what I'm going to call certifiable error rates. For that, I need to define what I'm going to call a certifier, or a sound certifier, which is paired with a learner. So a function, C, that takes in a bunch of unlabeled data and outputs a number between 0 and 1, I'm going to call it a sound certifier for a learner A, if for every marginal distribution that's allowed and every number of samples, this certifier outputs an upper bound on the performance of the learner in expectation. So the expectation, when the certifier sees M unlabeled points and spits out a number, the expectation of that is at least the error of the learner. So it should give me an estimate of how well the learner does just by looking at the unlabeled data, and its estimate should be sound in that it should be always a valid upper bound. So this is a sound certifier, it's for a particular learner. And one way to think about what sound certifiers are doing is that if the unlabeled data doesn't allow the certifier to distinguish a distribution D from another distribution D prime, where maybe A does really well on D but does poorly on D prime, then in order to maintain soundness, the certifier must overestimate the error of the learner. So again, this learner may be perfect for D, but C can't distinguish D from D prime and A does poorly on D prime, so the certifier must bump up its estimate, effectively taking the worst case over all distributions that you can't tell apart from your true distribution. Any questions? This is kind of the key definition, so now's the time to reflect on it. So this certifier will estimate the learner's performance on a distribution, but there's another distribution that is almost indistinguishable from this one, where the learner does poorly, the certifier must output something bigger. So now this allows us to define the certifiable distribution fixed error rates. Remember, distribution fixed error rates were epsilon sub d. Now I'm going to call this epsilon tilde sub d. This is the minimum over all learner certifier pairs of the certifier's estimate of the performance of the learner, okay, on that distribution. And when I say learner certifier pair, I require the certifier to be sound for the learner. So this is the best error that I can do on distribution D if I must certify my guarantee just from the unlabeled data. Same amount of unlabeled data. Any questions?
I mean, it seems a bit odd here. I mean, the way you wrote it, right? I mean, the algorithm and the certifier can depend on the D that you're interested in.
And that's exactly by design. This is a benchmark. This is not a.
You're okay, but you're saying that's fine for you, even though.
I want to compete with that, right?
Okay.
So it's kind of, I want to be ambitious. I want it to look like something hard to compete with. And I'm gonna get into this point now. So let's compare this to the distribution fixed rates, which smart learners compete with. This is the best learner for that distribution. This is a lot like that in the sense that it still allows me to design the learner specifically for the distribution D. So it is distribution fixed in some way, but it only credits the learners with what they can certify. So it's strong in the sense that it still allows me to, it's still something that's catered to the distribution, but it's a weakening of the original epsilon because it only gives you credit for the guarantees you can certify. So one thing that's not too hard to see is that this epsilon tilde is bigger than epsilon, right? Because it doesn't give a learner credit for how well it's doing, it's only giving it credit for how well it's doing and it can certify. So this is an easier benchmark to compete with. Right? And it can be, this inequality can be strict, making it strictly easier to compete with when the distribution D is indistinguishable from a D prime, which is much harder, let's say.
So why can't the certifier here, I mean, so the trivial certifier, which just uses a holdout, just the certifier runs A on half the data and uses a holdout.
It only looks at unlabeled data. It's only allowed to look at unlabeled data.
Oh, okay.
Right. So our motivation was, whatever your measure of performance, it should be a function of the unlabeled data distribution. You should be able to certify it before you go get labels, let's say.
No, but wait, but that's still fine. So C can just enumerate over all hypotheses in the class.
There's so many hypotheses in the class that one of them will lead you astray. You're right, this is something we were confused about too. There's going to be a hypothesis where you do well, and there's going to be a hypothesis that you do poorly if you enumerate all of them.
No, because of the word.
This is why I wanted to give this talk. This is actually really, it's exactly these things that make this really hard to interpret.
Sorry, one question.
Yeah.
So D prime is also some allowable marginal.
Yes,
Okay.
yes. Think of it as an arbitrary allowable margin.
Okay.
So effectively we're pricing in the hardness of distinguishing and we're saying compete up to that. So now I can define relatively smart learning. I'm going to try to compete with these certifiable error rates. Let me remind you the definition of smart learning. I showed this before. A learner is smart if its error on every distribution is within a universal constant of the best learner on that distribution. I'm going to relax this a little bit. I'm going to do two steps of relaxation. First, I'm going to allow, I'm still talking about smart learning, but I'm going to allow some blow up in the sample complexity. I'm going to say a learner is sigma smart if, where sigma is kind of a function that measures a blow up in sample complexity. If when I give it sigma more samples, it competes with the distribution fixed learner with m samples. So think of sigma of m as being like something like m squared, for example. But also for technical reasons, I'm going to allow an additional additive term eta here, where I'm going to allow the blow up to depend on eta, and I want to allow kind of an additive increase in the error of eta, as long as I can take eta to 0. This is kind of just a technical thing, so you can actually think of eta always being equal to 0 and ignore it, but for technical reasons we need it. So by giving your smart learner more samples, you could ask, okay, does this save me from the impossibility result? It doesn't. This doesn't change anything. The impossibility result of Darmstadt, Simon, and Zoreni survives this blow up. So nothing really changed here. But the important change is going to be when I change this epsilon to epsilon tilde. Replace distribution fixed error with certifiable distribution fixed error. And this is what makes a difference. So competing with certifiable errors and also allowing an increase in number of samples, that's what turns out to make this possible. Where really this is the important part, I would say. Any questions? So the most important change is I changed epsilon to epsilon tilde, but that turns out to not be enough. I have to do this kind of allow you to trail in sample complexity a little bit. Yes?
You said that you introduced eta for technical reasons.
For technical reasons, we would love to get rid of it. We might be able to, but we don't know.
That was my question.
But we can take it to 0 and the dependence on it is linear, so it kind of doesn't matter too much. Okay, so the way to think about this is that I want to compete with certifiable error weights, distribution by distribution, instance-wise, when I allow myself a blow up in the sample complexity as measured by this sigma. And remember, these certifiable error rates priced in this indistinguishability of distributions. And the reason we call it relatively smart, well, first we like the name, it was catchy, but also I want to think of this as smart relative to distribution fixed, certifiable error rates. Now, ideally, we have the sigma being something small, maybe polynomial in m and 1 over eta. What we end up getting is m squared over eta. But this eta, is mostly for technical reasons. So if it helps you wrap your head around it, think of eta as, think of there being no dependence on eta and think of it as 0 over here. It's interesting to see if we can actually make it 0, but that's kind of a technical point. Now, just like in smart learning, I can ask this question for distribution families or distribution free setting. And then I'm going to focus first on the distribution free setting. Questions? We have 10 minutes?
You have 5 left.
We started like 5 minutes. I'll try to wrap up in 10 minutes. Okay, so let me tell you my distribution free results. Our main result is a positive one. Every hypothesis class, whether PAC learnable or not, admits a order of m squared relatively smart learner in the distribution free setting. This is just hiding m squared over eta, basically, in this theorem statement. And not just any learner does this, but for those of you who do learning theory, you'll recognize the one inclusion graph learner, which actually achieves this. If you've worked with this learner, you have a sense that it's kind of data set by data set optimal. This theorem basically formalizes that, is one way of formalizing that. Here's the proof idea. if I imagine that I give you m samples, these black points from a distribution D. Let's say D is my true distribution, the blue one. I can't tell if these black points really came from D or from distribution D prime, where D prime consists of m squared points that are sampled uniformly from D. So think of, you're distinguishing the uniform distribution over D from the uniform distribution on m squared points, where those m squared points themselves are uniformly sampled from D. So why m squared? This comes from the birthday paradox. If I gave you something less than m squared, then these black points will have collisions, whereas otherwise they wouldn't.
Wait, sorry, the expansion here is in the sample size, not an epsilon. I'm a bit confused because your definition before the expansion was an epsilon, but
Right now I haven't talked about epsilon. I'm just saying with m samples, can I tell apart D
no,
from?
I understand, but in the result here then, how should I interpret this result? You're actually telling me that whatever you can do with m samples, I can do with m squared, or the other whatever I can do with
Right.
m samples,
But
you
up
can
to
do
the
with m squared.
certification, up to the certifiable.
Whatever I can certify with m samples, you can. But
Yeah.
your definition was like an expansion on epsilon. No? When you started, you said like, what's the factor on epsilon you can get?
Yeah, so I'm hiding a constant. Really, in our definition, there's also, it's sigma comma
Oh,
C.
so that's the sigma.
Yeah. I'm hiding it because I don't want to have too many symbols lying around.
Understand. This is fine. So
Yeah.
your expansion isn't sigma.
So I mean, the constant I think ends up being E.
That's fine.
Yeah.
That's fine.
Okay, so good. So I can't tell apart D from D prime, where D prime is, m squared samples, and then the black points are m of those. And that's from the birthday paradox. Since I can't tell D apart from D prime, I know that whatever my certifiable error rate is, because it prices in this indistinguishability, it must be at least the true distribution fixed error on D prime. So epsilon tilde of D is at least epsilon D prime, because you have to be sound, you have to basically, take into account the fact that you could be wrong, D prime could be the true distribution, so to be sound, you have to at least overestimate this, okay? And then I can increase the number of samples, you'll see why. This is at least epsilon sub D prime of m squared. This is the best error you can get on D prime with m squared samples, because increasing the number of samples only helps, okay? Now let's say I give my learner m squared samples. It basically becomes as if I gave it basically all the support, effectively all or most of the support of this D prime, and I asked it to predict a random point. The problem becomes almost as if I'm doing leave one out learning on m squared points. We know what the optimal leave one out learner. We know what the optimal leave one out learner is. It's the one inclusion graph learner, and that's where this comes from. Questions? So I can't distinguish D from D prime. That means my certifiable error rate, is at least the error of the best possible error on D prime. D prime is m squared points. I'm competing with m points. I give myself m squared points. I basically have the entire distribution except for my test point. Let's leave one-eyed prediction. I know how to do that. So here's an open problem. So we have a relatively smart learner. This is this one inclusion graph learner. This is a complicated learner, typically not tractable, not simple at least. Is there a simple learner that is also relatively smart? We don't know. We don't even know if ERM is relatively smart.
Didn't you show us before it's not?
I showed you it's not smart. I don't know that it's not relatively smart. I showed you that it's not smart.
You can certify that example?
In that example, the certifiable error rate is large in that example, so ERM does well, I believe. Yeah, because you can, if you see square root of n samples, whatever number of samples you have, the best you can guarantee is the distribution is spread out enough so that it's at least roughly uniform on m squared many samples. So in that example, I believe ERM happens to be relatively smart. Because the benchmark goes up to the extent that you can't tell that you're in the uniform distribution. But nonetheless, I suspect that ERM is not relatively smart. We don't know how to prove it. Turns out to be pretty tricky. We tried really hard. We set Claude on it for 2 hours. We got nowhere. But nonetheless, I think the answer is no. Even there, we could ask, what about any other simple learner, maybe one that's tractable or polynomial time computable relative to an ERM oracle? That, I think, is going to be a very interesting question. Okay, so we had that positive result. We also have a matching negative result. There is a class such that you don't have anything better than quadratic in terms of relatively smart learning in the distribution free setting. So this M squared blow up is the best you could possibly do. And the details of that are technical. I have to construct a pretty elaborate class and a family of distributions. For time, I'm not going to actually get into it, but it kind of looks roughly like this. So now let me get into the distribution family results. So we had a positive result for distribution free. Do we have one for distribution families? Under some conditions where your family is really smart, the result extends. For example, if your distribution family is only described in terms of the supports you're allowed to have, let's say you say, I allow every distribution over manifolds of this form, then the positive result extends, and you get the same, basically, M squared guarantee with the one inclusion graph learner. More interesting is when you allow more general distribution families. We have a couple of interesting negative results. There is a hypothesis class and a distribution family which has even a smart learner, but neither empirical risk minimization or one inclusion graph is relatively smart. So what this says is that you can sometimes be smart, but you need a carefully designed learner for the class. And the idea here is that the distribution family could be such that you could do some interesting unsupervised learning on it, which these kind of off-the-shelf supervised learners like ERM and OIG don't take advantage of. The thing you're confused about, I'm going to get to in the next slide. This is the most confusing result. There is a class and a distribution family such that no learner is relatively smart. And what this implies, because I have a relatively smart learning in the distribution free setting, this implies that the difficulty of relatively smart learning can go up and down as you grow up the distribution family. So this difficulty of relatively smart learning can be non-monotone in the family. This seems like a paradox that's been troubling Nati for a while.
No, the relatively smart, if the results are relatively smart, I'm fine. The previous was also just for, the statement is only for relatively smart also.
Which statement?
On the previous slide.
Yes, this is only about relatively smart.
Okay, no, relatively smart is fine.
But yeah, let me try and demystify it nonetheless. How could adding more distributions make your life easier? How could it be that in the distribution free setting you get relatively smart learning, but for a distribution family you don't? And the key thing to notice here is that my benchmark is now a function of the entire family. Even though the job of my learner gets harder when I add more distributions, but also the job of my certifiers gets harder because they have to be sound with respect to many more possibilities of what the other distribution could be. So certification gets harder, which can weaken my benchmark, and you have two competing effects. The learning task gets harder, and certification gets harder, and depending on which one's getting harder faster, the problem can get easier or more challenging. And that accounts for this non-monotonicity. Okay. So that's it for technical results. Let me just wrap up. I introduced this notion of relatively smart learning, which prices in this one versus many indistinguishability of marginals into smart learning. I have a general positive result in the distribution free setting, which allows quadratic blow up and sample, when you're given a quadratic blow up and sample complexity, and we showed that this is tight. I also showed a more nuanced picture in distribution family settings. You can require idiosyncratic learning approaches involving some unsupervised learning to get relative smartness. You can also get impossibility results, and that implies non-monotonicity of how hard it is in the distribution family. The more interesting thing I want to leave you with is future work. I like that this paper raises some very nice open questions. We don't know if ERM is relatively smart. I suspect the answer is no, but this turns out to be difficult to prove as far as I can tell. Assuming it's no, I think a very juicy question would be whether you can get a relatively smart learner in polynomial time relative to an ERM oracle. That seems tricky, and I would love to see the answer to that. You could also ask if there's in the distribution family settings, is there a general blueprint? You know, can I always break down relatively smart learning into some kind of certain kind of unsupervised learning followed by some supervised learning? That would be nice. That's kind of a how do you ask the question type problem. And a very interesting question has to do with domain adaptation, which is actually how we started thinking about these questions. We actually didn't set out wanting to understand smart learning. We wanted to understand domain adaptation, and we were trying to ask ourselves, is there something instance optimal I can say about domain adaptation? And then we realized pretty quickly that if I want to do it for two domains, first I have to do it for one domain, and that's what this paper does. So what I would love to get is some instance optimal learning with distribution shift, to say that instance by instance, or for every pair of domains, I'm doing as well as I can do at adapting my guarantees from one domain to the other. So that I think is very exciting, and we're already starting to think about that. And that's all I have. Thank you.
Okay, thank you. We have lots of questions, but we're a bit
Sorry about that.
over time. We take quick questions. Yeah, Aitan.
Thinking about distribution shift for the last 20 minutes, can I interpret the result as if you can certify distribution shift, then you can do better. But in the original framework, you cannot certify distribution shift. So basically, if you can detect a distribution shift, you can do better.
That would be like a really good case. That would be a really good result, actually. Really, that would be the best case scenario. But it's not about just certifying distribution shift. You want to. I think it might matter what the distribution shift to what. That might matter, right? I don't know that it doesn't matter.
With respect to a certain class. I mean.
Right. But let's say you can certify that there is a distribution shift, but you don't know the form of the distribution shift. Let's say you know that your first domain is D1 and there's a D2. You know they're not equal, but you don't know exactly details about D2 that will be relevant to how you adapt. It's not clear how much that matters. So there's a modeling question of how you ask that.
Last question.
Small question about the open question. So when you say ERM is not relatively smart or some other variant.
I suspect.
So not being relatively smart is with respect to specific sigma, right? So are you saying that for any sigma function this is not relatively smart, or there is some?
Yeah, any sigma that is a function of m and eta,
Okay.
such that eta can go to 0.
I see.
I would want it to not be relatively smart.
And for the positive result, I suspect you intend it to be sigma, which is some polynomial.
Yeah, and what we get is m squared over eta, but I mean, I think it would be still interesting if you show ARM is relatively smart with sigma is equal to 2 to the m. I think that would be surprising, but it would be interesting.
Just want to be clear. The thing is, like, if you fix eta to be something like just half, the definition is still interesting, right? Like,
well, no, half is like trivial to get, right? Because you can only get error half by the guessing.
I thought in your definition, you had epsilon. Oh, I see. Okay.
Yeah. You would want to take eta to 0 for this to be interesting.
Okay, let's thank Shaddin again.
Thank you.
And,